A very efficient way to modify surface tension consists in adding molecules having a tendency to adsorb at the interface. Such molecules are called surface active agents or surfactants. Here, we add a tiny amount of dishwashing liquid at the center of a water bath. Thin plastic discs floating on the water are expelled away from the place where the soap is added. The machine reveals that the surface of water moves radially. Again, this motion is due to a gradient of surface tension, the tension of the center, where we have surfactant, being lower than at the periphery, where water is pure. We have seen that dishwashing liquids modify the surface tension of water, and we would like to understand why surface tension agents, surfactants, modify the surface tension. So the question that we're asking is why surfactants change surface tension. First of all, we need to know that surfactants are molecules which have a peculiar characteristic of being amphiphilic. That is, they're made of two parts. So amphiphilic molecules. They're made of two parts. One part which is very often an hydrocarbon chain, which doesn't like water, so it's a part which is hydrophobic. It's difficult to dissolve in water. And another part which can be either an ion or a different chain more soluble in water, which will be hydrophilic. A good example of this type of molecule, which is often used, is called sodium dodecyl sulfate. It's essentially a 12 carbon chain, dodecyl, so it's a long chain made of 12 atoms of carbon, terminated by a sulfate ion here, and we have two balanced charges, a counter ion, which is sodium here. When I add sodium dodecyl sulfate to water, I get the following results in terms of surface tension. If I plot here the surface tension in millinewtons per meter, as a function of SDS concentration, I get the following results. I'm starting from the surface tension of pure water, which is 73 millinewtons per meter. And as I add SDS, the surface tension decreases until I reach a point at a concentration which is typically 8 millimoles. And then the surface tension is constant at a value which is around 38, that is typically half the surface tension of pure water. Now we would like to understand physically this type of behavior. To understand this curve, let us look at the behavior of the surfactant molecules when we add them to water. So I'm sketching here the water-air interface, and I'm adding SDS molecules. I will sketch like this. Some of them are in solutions, not in very large concentration because it's not very soluble. And a lot of them are on the interface in a way such that the hydrophobic part, the carbon chain, is outside water, and the hydrophilic part, the ion, is inside water. So these molecules organize at the interface like this. And when they are at the interface, they move because of Brownian motion, and they behave as a two-dimensional gas. And this two-dimensional gas has a pressure, pi, which is given by the number of molecules per unit area, n number of molecules divided by the area of the surface, multiplied by the thermal energy, kT. So this is the pressure associated with this two-dimensional gas molecules. Now if I had a barrier on the fluid, the molecules would exert a pressure, this pressure pi, on the barrier. In order to understand the variation of surface tension due to this two-dimensional gas, we will perform a virtual experiment in which we would move this barrier by a distance dx. On this side, we have the surface tension of pure water, gamma 0, and on this side, we have surface tension modified by the surfactant. The change in energy is related to the change of area of the two parts, which is gamma minus gamma 0 multiplied by dx, plus the contribution due to the work done by the pressure on the barrier, which is pi multiplied by dx. And if we are at equilibrium, this change of energy should be 0, so we get the result that the surface tension modified by surfactant is equal to the surface tension of pure water, gamma 0, minus the pressure due to the surfactants at the interface. So we understand that by adding surfactants in the liquid, the surface is populated by molecules, and as we increase the number of molecules per unit area, we increase pi, and we decrease the surface tension. Now we see that beyond a given concentration, the surface tension remains constant, which means that the number of molecules per unit area should remain constant. So this critical concentration is called the critical micelle concentration, and we will understand why. As we add molecules of surfactants into the liquid, at a given point, this critical micelle concentration, it becomes more favorably energetically to add molecules into micelles, that is, to create entities composed of surfactant molecules in which the hydrophobic part is hidden within the structure, and the hydrophilic part, that is the ionic part, is exposed at the periphery, exposed to the water. So beyond this so-called CMC, we gain more energy by creating micelles than by adding molecules at the interface between liquid and gas. So as a result, N remains constant, and since the pressure, the surface pressure, does not vary, we have a surface tension which remains constant. So we understood that we can decrease the surface tension by adding amphiphilic molecules within the liquid, but we'll see also that we cannot diminish the surface tension to a very low value, because beyond this critical micelle concentration, we can no longer add molecules at the interface, and as a result, the surface tension no longer decreases. Surface tension gradients can be harnessed to move solid objects at the surface of a liquid. Here, centimetric plastic discs, which are cut obliquely, are propelled by the dissolution of a small bit of camphor. Because of the asymmetry of the cut, the discs rotate. One is left-handed, the other right-handed, and they rotate in opposite directions. Camphor is a solid soluble in water that reduces surface tension. The tension gradient produces a torque leading to rotation. Since camphor is volatile, the surface of water is contaminated only locally, and the tension gradient is renewed as long as there is some camphor remaining.
Microvelia, a small insect living on water, is capable of moving on the surface using its legs, but when threatened, it uses Marangoni propulsion by releasing surfactant on the water while bracing its legs along its body, presumably to diminish the drag force. The typical velocity it can reach is 15 centimeters per second, often large enough to escape predators. Surfactants can also modify locally the interface between a solid and a liquid, as illustrated by the motion of a millimetric drop of octane deposited on a horizontal glass plate. The drop contains a fluorinated silane reagent, which absorbs on the glass and makes it less wettable. As soon as it is laid on the glass, the drop moves spontaneously. At the rear edge, silanes are adsorbed on the substrate, and the drop moves away from this non-wetting coating. The path is self-avoiding. The drop rebounds on tracks left on the glass. At the end of the motion, the wetting properties of the glass are revealed by a breath figure. Where the silane has been adsorbed, the mist is slightly darker. A drop of dense oil, nitrobenzene, is deposited on a stack of small glass plates immersed in a bath of water. Water contains a cationic surfactant which adsorbs the negatively charged glass and makes it hydrophobic. The oil phase contains an iodine compound, giving the orange color, which can associate with the surfactant to dissolve it in oil. As the drop moves on the adsorbed layer, it detaches the surfactant molecules, thus creating an asymmetry between front, still covered with surfactant, and rear, which is almost bare glass, hence a capillary force driving the motion. This depletion mechanism pulls the drop up the steps made by the glass slides. As soon as the drop leaves a bare spot, surfactant readsorbs on the glass, making it hydrophobic again, and allowing the drop to go over its previous track, as seen when the drop goes back and forth between the edges of the top slide.